Well, let's go ahead and now perform a problem in which we are able to look at uh, an example problem as it relates to conservation of mechanical energy. So the problem is, what is the finished speed of the roller coaster if its initial speed at start is 5.00 meters per second, assume no friction between the cars and the track? Okay, so let's point out a few things here. Okay, so, whoops. Here we have the roller coaster car, okay, and we're assuming that its initial velocity is not this right here, but its initial velocity is 5. So let's see here. So 5 meters per second. That's its initial velocity. We can also see that the height below the bottom of the big hill is 25 meters, and the height below the top of this plateau is 20 meters. We want to know the finish velocity. So this is our question mark. Okay? Now notice the angle of the slope of the roller coaster is constantly changing. So if we were to use Newton's laws, this would be quite a difficult problem. But one of the things we find is that if we are going to pursue conservation of energy, that makes this problem quite a bit easier. Okay, so with conservation of energy in mind, let's write down the conservation of mechanical energy. So I'll start this problem up here. So I think the conservation of mechanical energy is the principle we want to use. Conservation of mechanical energy. Okay, so the conservation of mechanical energy should be the following: that the initial mechanical energy is equal to the final mechanical energy. So ME initial is equal to ME final. Okay, so if the mechanical energy is conserved, this is the conservation equation that we have. Conservation of mechanical energy. All right, so the mechanical energy is going to be the sum of the kinetic energy plus the potential energy. Now the potential energy in this case is gravitational potential energy. So let us just write this in its more expanded form. The initial kinetic energy plus the gravitational potential energy initial, put a comma there, is equal to the final kinetic energy plus the gravitational potential energy final. Okay, so this is exactly the conservation of mechanical energy for this problem. Now for this particular problem, we want to start to expand it out because we're looking for the final velocity here. So we have to get velocities out of kinetic energy, and then we're given information about height, so we want to expand out the gravitational potential energy terms. So what that means is 1/2 mv initial squared plus mgh initial should equal to 1/2 mv final squared plus mgh final. Notice a couple things. First of all, the kinetic energy term is the same except it's initial and final for the velocity. Let's assume that the mass does not change in this problem. And then furthermore, the height is initial and final for the initial and final gravitational potential energy terms. Now I want you to notice something that's important. Okay? Notice that I'm changing colors intentionally because something interesting is going to happen. have a look at these terms and note that there is one term that is going to drop out throughout the entire equation. You might want to pause the video and think about that. So it's going to be mass. Hopefully you see that mass drops out of this conservation of energy equation. So I'll write that. I'll write that this equation is, and remember, whenever an entire value drops out, this equation is independent of mass. Okay, so independent of mass. Whoops. Independent being the key word. Okay, so independent of mass. Remember, independent means the mass doesn't matter in terms of the final result. Another way to say this is that if you had more mass, you'd expect that you'd have more kinetic energy and more potential energy, but it would be harder to build up the final kinetic energy and the final potential energy. So it's like nothing gained, nothing lost, so the mass goes away in this problem. All right, you can imagine multiplying the entire equation by 1 over m. That would cause this to go away. And then one more thing, let me also say it's going to be much better mathematically, easier to see, if we take this equation and we multiply everything by a factor of 2 on both sides of the equation. Why? Well, if there are 1/2, we can eliminate all fractions by multiplying both sides of the equation by 2. All right, so let's write down what we have remaining. Okay, so what we have remaining is, I'll write it over here, let's see, v initial squared plus 2, that's a plus, 2gh initial is equal to v final squared plus 2gh final. Remember, v here is velocity, g is the gravitational constant for Earth, and h is the height. Okay? Now, what we should do is we should solve for the final velocity. So in order to do that, we need to subtract this term over with a minus, and then I think we need to take a square root. So let's see if we can just write that. That's v initial squared plus 2gh initial minus 2gh final is equal to the final velocity squared, so we'll take the square root. So let's take the square root of this. And by the way, all we really want is the speed. So let me try to write this as best I can. Let me get a nice straight line here. Okay. So all we really want is the speed, so I'm not going to worry about the plus and minus in front. So we just want the speed. And by the way, if you want to, you could also write this term as 2g times h initial minus h final. Because think about this. The final velocity depends upon the initial velocity, but it also depends upon what the height change is. That's h initial minus h final. Now, by the way, we should define what h initial and h final are. So let's see. Suppose we call, let's do this in two separate ways. Suppose we call the initial height here, suppose we call this 0 for height. So this right here is h equals 0 meters. If that's h equals 0 meters, so remember, we are free to choose the initial height, or that is the 0 height for potential energy. That means the initial height, I think, is 25 meters, and the final height is 5 meters. So if we do it this way, then height initial is 25 meters, and then height final is 5 meters. Okay, so this will give us 25 meters minus 5 meters. Now, by the way, part of the reason I chose different colors is because you may ask, well, what if you want to do the problem in a slightly different way, where you defined h equals 0 as the plateau here, h equals 0 meters. Now, you could do that because we don't really care about the speed at the bottom of the big hill. We care about the final speed as the car finishes. So what you could do is you could say that the height initial above this plateau is 20 meters. So that would be height initial equals 20 meters, and then height final equals 0 meters. Now that works fine. That makes the calculation for this problem easier, but I would caution you, if you're going to do a second calculation where you want the velocity at the bottom of the big hill, you don't want usually a negative height for gravitational potential energy. So I would recommend setting this to be h equals 0, like I'm showing here in green. But anyway, let's go ahead and just use what's in green, and then let's switch back and perform our calculation by putting the numbers in. Okay, so let's get our final velocity here. So let's put all the numbers in. So it's going to be big square root, and again, let me hold down shift to get a nice straight line. Okay, so this should be the initial velocity squared, so that's 5.00 meters per second squared, and that's going to be plus 2, and then g is 9.8 meters per second squared. And let's just multiply it in this form where we've factored that out, and then we'll do h initial minus h final. So h initial is 25 meters minus 5 meters. Okay, so there we go. So let's get this v final. Okay, and when you calculate that, do that in a calculator, you should get about 20.4. That's what I got, 24.4 meters per second to 3 significant digits. Okay, and let me see if I can put a nice box around this. Okay, so this should be our final answer, the 20.4 meters per second for the final speed of the car as it goes down the plateau, using conservation of mechanical energy. Okay, that ends this problem and this video. Thank you very much for your attention. I will see you in the next video.